as Earth is a very big sphere and its capacity is very less. As I told you, the capacity of Earth is only 711 microfarad. So I am starting with the capacitor. What this capacitor actually is? The capacitor is an arrangement of two insulating conductors separated by some finite distance and the medium between them is some insulating medium, or you can say capacitor is an arrangement to store large charge, or we can say energy, in small volume. So here you can see Earth is a very big sphere and its capacity is only 711, that is 711 microfarad. And so if we want to store the very large amount of charge, then we need the capacitors. The capacitor, that is an electrical device that is used to store the large amount of charge or the energy, you can say, in very small volume. And we can also define the capacitor, that is the arrangement of two insulating conductors separated by some finite distance and the medium between them is some insulating medium, or you can say arrangement of the conductors to be separated by some insulating medium and to store the charge. So the capacitor here, the device that is used to store the charge, and you can say to store the electrostatic potential energy. Suppose here is a conductor, here is another one conductor. Suppose this one is to be given a charge Q. The charge on the very first conductor is the plus Q, suppose, and on another one, that is the minus Q, suppose. Here is the charge minus Q, and they are to be separated by some finite distance. The potential of this one is the positive and the potential of this one is the negative. Let V is the potential difference between them. V be the potential difference between them. You know Q directly proportional V, and Q that is equal to C into V, C that is equal to Q by V. Here C is the electrical capacitance of the capacitor. And you can categorize capacitors on the basis of their geometry. Capacitor can be classified in following ways. One on the basis of geometry, and the very first one is PPC, parallel plate capacitor. This one is the classification which is based on their geometry, and geometric classification, very first one is the PPC. This one is a geometric classification. Second one is spherical capacitor. And next one is the cylindrical capacitor. and many more. And we can also classify them on the basis of the medium between them. Between the plates, suppose air capacitor, ceramic, mica, electrolytic, etc. So the capacitors, they can also be classified on the basis of the medium between the plates. Suppose one is the air capacitor, second one is the ceramic, mica, electrolytic or paper capacitor, etc., etc. So here are the many more categories, and also symbolic representation. This one is the plates of a PPC, and this one is a fixed capacitor. Secondly, this one is a variable capacitor. Here the capacity is fixed, here the capacity is not the fixed, and we can classify them on many more bases. So the capacitor, that is the arrangement to store the large amount of charge in the small volume. So here I am writing the principle of a capacitor. To understand the principle of a capacitor, let us consider one plate. This one is a plain plate, and let this one is to be insulated, and this one is placed on some insulating material, and let the charge that is given to the plate. When we are giving the charge to the plate, then its potential also rises, because Q, that varies directly proportional to V. So as the charge increases, so the potential of the plate, that also increases. One stage reaches when the potential that becomes maximum. A stage reaches when the potential of the conductor becomes maximum. After this, if we try to give more charge to conductor, charge start leakage. जो चार्ज है वो लीक होना स्टार्ट हो जाएगा, एंड यू कैन से द मोर चार्ज दैट कैन नॉट बी गिवन टू द कंडक्टर. सपोज नाउ I am bringing another conductor that is close to the given conductor, then a neutral. This one is a neutral. By the induction method, the negative charge that rise on the near face and the positive charge that rise on the farther face. Here negative charge induces on the nearby face, and positive charge induces on the farther face. When a conductor is placed near the charged conductor, this induced negative charge tries to reduce the potential of the plate A or the charged plate, and positive charge tries to enhance the potential of plate A, that is the charged plate, as the negative charge, induced charge is comparatively closer, so the potential of plate A decreases. So you can say this one is the plate A and this one is a charged plate. This one was the neutral. When we place this neutral plate closer to this plate, then here the negative charge induces, here the positive charge induces on the further face. This negative charge that tries to reduce the potential, and this positive charge this tries to enhance the potential. So the net impact is of the negative charge, because this one is comparatively closer in comparison with the positive charge. So this potential of this plate that decreases a little bit. So you can say now the potential becomes V minus dV, and the additional charge can be given to the plate A. So we can add a little bit charge on this plate. So the charge you can add, that is dq. Now if we earth the plate B, that is this plate, on earthing this plate, electrons neutralize the positive charge. We earth the plate B, electrons from earth neutralize the positive charge, positive induced charge of plate B. So the potential of plate A decreases by large amount, and additional charge can be given to the plate. And this one is the basic principle to add the charge on the plates of the capacitor. When we earth, the electron flow from earth and neutralize this all positive charge, and the potential of this plate that decreases comparatively large by large amount, and the additional charge that can be given to the plate. So this is the basic principle for the capacitor. So the capacitor, that is the arrangement, you can store the tremendous charge on the very small volume, you can say. And one more thing the student have to be remember, that I told you so that the capacitor, that is the arrangement to store the charge as well as the energy, the charge that is stored on the plates. You have to note down one thing very importantly over here, that the charge is always stored on the plates, but energy in the medium between the plates. So now we will discuss the very important one topic, the capacity of a parallel plate capacitor. So here I am writing the expression. It's a very important one question. Capacity of a PPC, that is the parallel plate capacitor. Here we will discuss the capacity of the PPC, that is the parallel plate capacitor. Consider a PPC parallel plate capacitor with the plate area A, that is the plate area. Let us consider a PPC with the plate area A and small d is the separation between the plates of the capacitor. Let plus q is the charge on plate and minus q is the charge on the another plate, and d, that is the distance of separation, and let the medium between the plate is the vacuum. The medium between the plates is the vacuum. Plus q is the charge on one plate and minus q is the charge on another plate, and v be the potential difference. Plus q and minus q be the charges on the two plates respectively, and v be the potential difference between the plates. So you can say V, that is the potential difference between the plates. V is the potential difference between the plates. As you know, the electric field between the plates intensity between the plates of the capacitor is given by E, that is equal to sigma by epsilon naught. We have studied this result in application of Gauss theorem. This is the result from the application of Gauss theorem. So E, electric field intensity between the two plates, that is given by sigma by epsilon naught, also from potential gradient E, that is equal to V by D. I'm writing the magnitude of over here, neglecting the minus sign. So here are I do have the two equations for the E, and on comparing from equation 1 and 2 we get sigma by epsilon naught, that is equal to V by D. V is the potential difference and D is the separation, and this one is the result from the potential gradient. Sigma by epsilon naught, that is equal to V by D. As you know, sigma, that is charge per unit area. So Q, charge per unit area, by epsilon naught, that is equal to V by D. As you know, Q is equal to CV implies C, that is equal to Q by V. On rearranging the equation, this equation, if interchanging these two, we will get Q by V, that is equal to A epsilon naught by D, and this Q by C, you can write C, that is equal to A epsilon naught by D. So here is the capacity of a PPC in vacuum. This one is the result which is applicable for the vacuum only. So capacity of a PPC depends Number one, directly proportionally to the area, plate area. Secondly, that varies inversely proportional to the separation between the plates. And third one, C, directly proportional to epsilon naught, that is the permittivity of the medium or depends upon the medium. So here are the three factors on which the capacity of a PPC, parallel plate capacitor, that depends. Now, for some medium, C in medium, we can write A epsilon by D. Epsilon is the permittivity of the medium. And you know, epsilon are dielectric constant, that is equal to epsilon by epsilon naught. So implies epsilon, that is equal to epsilon naught epsilon r. So C in medium, that can be written as A epsilon naught epsilon r divided by D. You can replace epsilon r also by the K. So C in medium, that is equal to A epsilon naught K by D. Epsilon r, that is also the K. This one is the dielectric constant. So the capacity in medium, that is equal to K times the vacuum. In some medium, the capacity of a PPC, that also increases. So thank you.